Okay, welcome back. Happy Friday. First, a very quick announcement. This is one of the rare times I make no eye contact with everyone, so I'm going to stare at the floor. Today is the last day to withdraw from any class here at GCC, so if you are considering withdrawing from a class, try to find your academic advisor today. If you are considering withdrawing from this class, find me like right after class, and I can give you my opinion about your chances for passing the class. But end of day today is the last day to withdraw. Any questions? Okay. I don't stare at people. I don't make eye contact because then they think I'm talking to them specifically. So why is Ian telling me to drop the class? Does he keep looking at me? Okay, one more announcement on the regression project, which I know some of you have already started, which is great. There's a graph on the back of the first page, and one of the lines in that graph is not graphed correctly. It's not a big deal and it doesn't affect any of your calculations, but if you're really on the ball, which several people were on Wednesday, they recognize that an answer they got in the table did not jive with the picture, and that was because the picture was wrong, okay? So like, don't worry about that little detail, and it might not even come up for many of you, but something in the chart doesn't quite match the picture, and it's because the picture is wrong. Australia is supposed to be above that middle line, not below. Okay. All right, I think that's it for announcements. Let's go ahead and take a look at our calendar. Today is November 7th. We talk about something called related rates. Related rates are a very big and hard topic in calculus, and in fact, we spend 2 days on them. But Caitlin and I decided to split up those 2 days. So Monday, we're going to do a completely different topic, linear and quadratic approximations, and then we'll come back Wednesday and do more related rates. So this will give you some time to digest because this is a very complicated process that we're going to use to solve these tough problems. So that's what's happening there. One more thing about the calendar. It won't affect us, but this coming Tuesday is Veterans Day. There are no day classes on Tuesday. So if you have day classes Tuesday, they are canceled. All right? Questions on the calendar? Okay, so let's go to the top of page 9 and the daily summary. Can we go to, who's ready? Haley? Okay, so we're going to go through a guideline that's on page 3 of this packet, then we'll come back here to page 9. So go back to page 3. And we're just going to look at these two columns. The left-hand column is the general process to solve these new problems for today. The right-hand column is an example problem worked out step by step. We'll look at both columns, and I'm just highlighting right here that you're going to have this page with you when you take the tests and the quizzes, okay? So this will be in front of you. All right, first step here. It says a related rates problem is one where you're trying to find a rate of change, and the situation involves different rates of change that are related to each other. So for example, looking at the right-hand column, we have a 6-meter ladder leaning against a wall. Its bottom is being pulled out from the wall at a constant 0.5 meter per second. As a result, the top of the ladder slides down the wall. Can we imagine this? And we want to know how fast the top of the ladder is sliding down the wall when it happens to be 5 meters up the wall. So we're imagining this situation. You got this wall right here and the ladder kind of smack up next to it. And then we're going to pull out the bottom at a constant 2 meter or 0.5 meter per second. And as a result, the top of the ladder slides down this wall. And it's possible that the top of the ladder slides down the wall at a constant rate. After all, this bottom is being pulled at a constant rate. But it's also possible that it slides at different rates. So do we have any intuition here? Do we think it's going to slide down is the top going to slide down at a constant rate? Or is it going to be fast then slow? Or is it going to be slow then fast? Faster and faster, slow then fast, I think is saying the same kind of thing. Yeah, so I think our intuition here is right, that it's going to go slowly in the beginning and then fast towards the end. Step 1 here says read the problem, so it might require reading the problem several times. They're often quite involved. Step number 2 talks about defining variables, and then step number 3 says draw a picture. And so here's the picture. And there's an important thing to note here. All right, so first of all, this is the ladder, which is 6. This is an x and this is a y. How much is the y that's a part of this problem? Or what did I say? I said when the top of the ladder was 5 meters up. So it sure feels like that's just a plain 5. But the fact is, if you fix that at 5, then you're also fixing this side at some number, and you have a static diagram with nothing changing. And so you're not allowed to put the 5 here, because if you do that, you fix everything in the problem and nothing moves. So we need to have variables, which eventually will get fixed, but we're not there yet. So it's important to distinguish what's changing and what's constant, even if you've got extra numbers in the problem that you don't use initially. How come I don't need to call this like a general z? It's 6 meters all the time, right? That's the ladder. It is not changing. So you put constants for things that are always staying exactly the same. Anything that's changing has to have a variable, even if there's a specific value given to you. Okay, step number 4, so start writing things down in symbols. So when we talked about the ladder sliding out at 0.5 meter per second, would you guys agree that's a rate of change of this length x? And so symbolically, dx dt represents how fast x is getting bigger as time passes. And so almost every time, time is our independent variable. Time is the thing that's driving everything. And in this case, it's 0.5 meter per second. Is it positive a half or negative a half? Why is it positive? Because the ladder is going further to the right. So this x is getting bigger. But if this problem were going in reverse, you need to put a negative or you're going to get the wrong answer. So make sure that you're aware that these numbers could be negative. Then we determine and symbolize what rate we're trying to find. So going back to the problem, it says, how fast is the top of the ladder sliding? So it's talking about this vertical distance. What letter did we use for that distance? There's a y, and so the question here is asking us how is y changing, and symbolically that's asking about dy dt. Right? dy dt is the actual rate of change that we're talking about. And so in number 5, we recognize that dy dt is the unknown. That's what we're after. Do you expect dy dt to be a positive number or a negative number? Negative. Couple votes for negative. Other votes? Y dt, is it positive or negative? It depends solely on what's happening to the length of y. Mm-hmm. So, but the question is, what's happening to this y? Is it getting bigger or smaller? It is getting smaller, and if it's getting smaller, then it is changing negatively, right? This length is decreasing. So we expect dy dt to be negative, and it will when we're done with this problem. Step 6 is often one of the hardest ones. It says find an equation that relates all the stuff that's in the problem. Going back to my diagram, we need to pull out of a hat a relationship, an equation that relates those variables in that number 6. What equation can we pull out of a hat here? We can use a Pythagorean theorem here, right? Those things, those x, y, and 6 are governed by the Pythagorean theorem. So that's the relationship. But it just comes out of nowhere. And sometimes it's Pythagorean theorem, and sometimes it's like a trig function, like sine or cosine or tangent. Sometimes it's like a volume formula from your distant past. You just have to hunt around and hope to come up with some relationship between the variables and the numbers. And so x squared plus y squared equals 6 squared. Again, it might be tempting to change the y to, what was the number that was given for how tall it was? 5. Could be really tempting to do that. If you do that, you are fixing everything and nothing moves. So you cannot plug in here, not yet. But what we can do is take a derivative of both sides. And so that's what it says here. Differentiate implicitly, where the independent variable is almost always time. So we take a derivative of everything with respect to time. Last class was when we did implicit differentiation, and we said you take your derivatives of x things normally, but anytime you take a derivative of a y thing, what do you have to tack on? Was that dy dx, right, or a y prime at the end, because we were imagining that y was a function of x's. Here, we're imagining x and y completely separate from each other, both of them being functions of time. So now every variable here is changing as a function of time. So every variable gets a dt in it. So what's the derivative of x squared normally? Is 2x. But x has time underneath it, even if we don't have an explicit formula for it. So we tack on the derivative of the stuff, the derivative of x with respect to t. What's the derivative of y squared normally? 2y. But also y has t's inside of it. Every variable has t's in it, so we put a dy dt. So really you don't want to get in the habit of always putting a y prime because dy dt gives more information. It's saying y has t's underneath it, just like this tells you x has t's underneath it. What's the derivative of 6 squared? 0, right? It's not 2 times 6. It is a constant, so it's 0. Okay, next page. And it says, you know what, I'm going to come back for just a second to the bottom of this guy. Let's start plugging some things in. I see 4 different variable things here: x, dx dt, y, dy dt. Some of them we already know. So name one of these that we have a value for. Okay, so dx dt is really 0.5 or a half. What's the other thing we know? Is the y is 5. Only at this point, after we've taken our derivative, is it okay to plug in that 5. So that means we still have 2 things that we don't know. There's the x and the dy dt. Now one of them is what we're actually after in this problem. Which one was that? It was the dy dt, was up here. That's what we want. So the only thing we have left to find and plug in is which letter? Is the x. So all you got to do is figure out how much x is. How are we going to figure out how much x is? Well, you're going to use the Pythagorean theorem. Because when you fix the problem at a 5, then you can use Pythagorean theorem to find this other side. So we know that x squared plus 5 squared is 6 squared, right? So x squared must be 11. Square root of 11, we type it on the calculator, about 3.3. And so that 3.3 goes in for which letter? Goes in for the x. So does everybody see this equation in 9? Do we understand where all the pieces came from? I'll rewrite what it was before. It was 2x dx dt plus 2y dy dt. Equals 0. So we substituted for 3 of those things, and the 4th one is the dy dt, and that's all that we're after. Questions on the equation in 9? Okay, and again, the goal was to solve for dy dt, so here it's just a little bit of arithmetic, or algebra, I should say, to get dy dt by itself, right? You've got this 2 times 3.3 times a half. That's one number which we'll type into the calculator, but all of it goes over to the other side by subtracting. And then you have the 2 times 5, which goes over by dividing. And so when you crunch all the numbers together, it turns out about negative 0.33. Let's get some units so that that number has meaning. The units for dy dt, remember, are the units for what variable? Yeah, the y variable over the t units. What are the y units? Meters time seconds. So that is negative 0.33 meters per second. Again, we were expecting a negative number, which we got because the y distance is getting smaller. So the ladder is falling at about negative 0.33 meters per second, just at that one instant where the ladder is still like 5 meters up the wall. So in order to figure out if our intuition was right, we thought it might be like falling slow and then faster, faster, faster. We need another number for comparison, right? So let's see if we can answer this same question again, but instead of doing when the ladder is 5 feet up the wall, we'll look at when the ladder is 3 meters up the wall and then 1 meter up the wall. So this isn't going to be too hard because we've already done most of the work. Again, I'll write down the basic equation that we had from the previous page. All right, let's start plugging in. The dx dt we know is still 1/2. This 2 is still sitting in there. I'll leave a blank space for the x. I don't know it yet. Plus, yeah, those will cancel. 2 times. Okay, now we need the y. The y has changed. We're doing right now the 3 meters up the wall part. So how much is y? It's 3. Are we looking to substitute something for dy dt? No, that's the unknown we're solving for. So we'll just copy that guy straight down. So what's the only other thing left for us to plug in to substitute? Is that x that's there in the middle. And in this example, we know that we've got an x here, a 6 here, and now we're fixing y at how much? 3. And so how could we find x? Pythagorean theorem, right? So x squared plus 9 equals 36. X squared is 27. Square root of 27. So we take that 5.2, put it right there. Any questions on those pieces? Okay, and then it's not very much algebra to actually solve for dy dt. So the first stuff multiplies to just 5.2, which gets subtracted to the other side. 2 times 3 becomes a 6, which gets divided. And maybe without rounding that 5.2, can somebody give me an approximation here? Okay, so minus 0.866 meters per second. Remember, the first problem that we solved here was when the ladder was 5 meters up the wall and it was falling at about 0.33 meters per second, and now it's further down the wall, falling at negative 0.866. So is it falling slower and slower or faster and faster? Faster and faster, which is what we expected. So I know that this problem also says do 1 meter up the wall. It's the same calculation. We'll get an even bigger negative number. Let's save time and not do it here. Any questions on that process? Don't worry, we're going to do 3 more related rates problems together this class. So we'll have lots of practice with that process. You're getting ahead of us, but eventually. Okay, so let me, I'm going to pull up a geometry sketchpad thing. Have we looked at sketchpad before? Maybe once or twice I pulled it out, I don't know. This particular piece of software, you can see how nice it looks. That's an indication that I didn't make it. So this was made by Audrey Weeks, and I think it's really great. So first we're going to slide the ladder. And there's a lot of stuff changing, but the only thing we want to focus on initially here is just this distance, and just verify that it looks like that distance is changing at a constant rate. You guys buy that? Looks like it's changing constantly. And now we can look at the vertical distance and ask ourselves if it looks like that's changing constantly. No, it doesn't. And we can see very slow changes, very small changes in the beginning, but then faster, 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 and then it just slams down at the end, right? We can hardly even see it, it's so quick. And so what we can do is we can take a look at the derivative of y with respect to t. I think this is what we got initially, right? When we were 5 meters up the wall, and if we zip, so that's at this moment, and then if we zip to the place where we're 3 meters up the wall, right, x changed to 5.2, and we got that. If we had done the other calculation, it would have been almost negative 3 meters per second, right? Really quick. Okay, so we'll come back to Audrey's beautiful application in a few minutes, but let's move on. Let's go back to page 9, and we'll try number 2. Andy, can you read 2, please?
A boat is pulled into a dock through a pulley that is 20 higher than the bow of the boat. If the rope is pulled at a rate of 2 feet per second, how fast is the boat approaching the dock when there are 30 feet of rope out? How about when there is 20 feet of rope out? Round your answer. Here's 100.
Okay, so let's draw a picture here. This right here is my dock, and we'll be real fancy and put the water in blue down here at the bottom. And so we've got this boat sitting out here in the water someplace. I'm not going to lie, that's a pretty sweet boat. And then it's being pulled in, from somebody up there at the dock. And so we've got this rope that is up here and connected directly to the boat, right? And so we're going to pull that green rope in, and the boat is going to come towards the dock, yeah? And it says that we're pulling the green rope in at a constant rate of 2 feet per second. So just somebody pulling constantly 2 feet per second. So that means the green length is getting shorter 2 feet every second, okay? So before we do any variables and derivatives and stuff, just looking for intuition. Do we think that the boat is going to approach the dock, which is this horizontal distance on the water? Do we think the boat is going to approach the dock at a constant rate because the green is getting smaller at a constant rate? Or do we think the boat is going to approach slowly then faster? Or do we think it's going to be fast and then slow down as it gets close to the dock? Fast and slow. Heard a couple of slow then fast. We heard a constant. We've got all our bases covered. So let's see what happens. So we're going to start putting in some letters and numbers. So first of all, this distance right here is given. How much is it? 20. Where is the bow of the boat? That's at the top? No. All right. My picture needs amending, I guess. So the bow of the boat is there. Okay, so we've got this distance right here is 20. Is it fair to call it 20, or should we put a letter on there, a variable? It's always 20. So don't make more variables than you need. And then it seems like it's a very natural thing for us to draw in that horizontal. I'll make it a different color because this horizontal distance is going to give us a sense of how fast the boat is approaching the dock. So that's what we're after. And then that green length. There's a number in this problem that tells you how long the green is. How long is the green for the first part of this problem? It's 30. So it feels like we should put a 30 there. But we can't. Yeah, it's just too early to fix. If you fix it, then nothing moves. So you got to put a variable there, even though we know that at some point it's going to be a 30. So I'll call it a z. And the red distance we can call a y. Call it x. It's horizontal. Doesn't matter. But those are our two variables. Now we need to pull out of a hat some relationship between those three things. It's the same trick that we used in the last problem, Pythagorean theorem. So we go 20 squared plus x squared equals z squared. And then we'll take a derivative of both sides with respect to what underlying variable? Nope. Time. For these kinds of problems, time is almost always the thing that's underneath everything. Okay, so what's the derivative of 20 squared? 0. Derivative of x squared? 2x times the x dt equals, what's the derivative of z squared? To z dt. And so with just a little bit of practice with these problems, we start to recognize, oh, just every variable, you got to slap on one of those dt's. All right, let's make our life a little bit easier and cross off those 2's. Divide both sides by 2. Okay, and now we got to start maybe I jumped the gun here. So at some point we got to know what we know and what we're trying to find. So let's look at the first thing here, the rate of 2 feet per second. So symbolically, something is 2 feet per second. What's the thing that's 2 feet per second? Yeah, because it's the rate at which z is changing by 2 feet per second. So it is a dz dt. And I'll ask the same question I asked before. Is it positive or negative 2? Levi says negative because green is getting shorter, right? So it's decreasing in length, negative. Okay, and then let's symbolize the thing that we're after. So it says here, how fast is the boat approaching the dock? That's what we're after. That is dx dt. Right, because x is the horizontal distance. We want to know how fast is that boat coming towards the dock. Okay, so now I think it's time to start plugging some stuff in. So using our derivative equation here, we're going to change the x to a certain number. I don't know what that number is yet. What's the dx dt? We don't know, that's what we're after. Okay, so we'll copy the dx dt. Equals, how about the z? 30, right? And the z is 30 feet of rope out initially. dz dt, negative 2, that's from there. The other thing we need to plug in is what? Is the x. So you got to find x. But at the moment, when the green is 30, we can find x. So let's find x. 20 squared plus x squared equals 30 squared, right? That's when we're going to find x, by plugging 30 into that Pythagorean theorem equation. So let's see, 400, 900, so 500 altogether. Square root of 500. Let me guess on this one. 20, 22, 22 and change. Okay. So that can go right in here for the x. And then finally, to solve for dx dt, what do we do to both sides? Good. So 2.8, 0.68. And again, units are helpful. This is a derivative, so the units are the top units over the bottom units. X is measured in meters. T is measured in second. So looks, oh, feet. Thank you. Thank you. So that red distance is changing by about negative 2.68 feet per second. That's the rate at which the boat is approaching the dock, the horizontal rate. Does it make sense that that red derivative was negative? Yes, because red is getting smaller. Questions on that? Okay, to test our intuition, we want to answer the other part of this question, which is when we have 22 feet out instead of 30 feet out. So can we give you guys maybe 90 seconds to try to answer that follow-up question? Check in with each other. Okay, questions on that? It's kind of nice once you've done one, like once you've done the problem all the way out, then tweaking the numbers is very quick to do, right? You don't have to start over. So we do get to test our intuition. So when the boat was farther out, it was coming in at about negative 2.68 feet per second, but as it gets closer, it was like negative 4.8. So this feels like one of those fast then slow then fast type things. So Audrey Weeks came up with another nice visualization. Here it is. So we're going to reel this boat in. The first thing I want you to do is just look at the green and convince yourself that it looks like green is changing at a constant rate. It was supposed to be 2 feet per second, right? I think that these guys are spaced out 2 feet. So they're only there to help us see that the pulley eats these guys at a constant rate. So just watch the green. See if you buy that those are getting eaten at about a constant rate. Reasonable? Okay, and now we're going to look at this blue, this x of t, and we're going to ask ourselves if that is going constantly, and we could see no, it's going changing pretty slow in the beginning, and then wham, you know, just like crashing into the dock. It's been a long time since I've seen Speed 2, but was there a boat crashing in a dock in that one? I think we'll have to, we should go watch that one. All right, so then we can look at the derivative. We did it right here. We got negative 2.68 at that moment when we were 30 feet out, and then when we were only 22 feet out, we got the negative 4 point. Is that what we got? Yeah, great. And then if we're 20.5 feet out, what does that mean about, like, if the rope is 20.05, where's the boat? It's like basically on the dock, right? Because it's 20 there, and the hypotenuse of this triangle is just a tiny bit more than 20, and there the boat is cruising at negative 28 feet per second. All right. Next page, we'll do our first one. So let's try number 3 here. This will be our first one that doesn't use the Pythagorean theorem. I don't want you to get the sense that everyone uses Pythagorean theorem. Okay, let's go to Cameron for 3. Okay, so we've got this cone, so I've drawn it up. I guess I'm better at drawing cones than boats, but so we've got our cone, and we're going to fill this cone up with water, and the water is coming in at a constant rate, that 2 cubic centimeters per minute. So basically, just imagine filling your water bottle at one of these water fountains or something, right? Basically, the water comes in at a constant rate. But now imagine your water bottle is in the shape of a cone, not like a cylinder, and so we're going to be thinking about how fast the water level is rising, so going up this way, when the water is 5 centimeters deep and 10 centimeters deep and 15 centimeters deep, which is just about the top of the cone. So do we expect the height of the water to rise at a constant rate? Or do we think it's going to be slow and then faster, faster, faster? Or do we think it's going to be fast and then slower, slower, slower? Fast and then slow. And this one, I think we all have intuition, right? Because we can just see there's just not that much space at the bottom. So it's going to fill up fast in the beginning and then slower at the end. So let's use calculus to describe those relationships very precisely. So we need some variables here. So let's get some variables in. So how about we'll put the water there. Now, so should I label this distance right here as 5 or 10 or 15? What should I put there? We are doing 5 first, but we should put a variable right there, right? If you put a constant there, then no water is coming in. I'm going to call it h for height. Okay, so there's our variable. We're also given some information about the entire cone. It says the height is 16, so it seems like that's useful. I don't know exactly why yet, but go ahead and label the 16 there. And then the radius at the top is 4. Okay, and now we need some formula that's going to relate some stuff together. And we're given this kind of funny information here that we haven't written down. That the water is coming in at 2 cubic centimeters per minute. So what mathematical property of that cone are we describing with this 2 cubic centimeters? We're talking about a volume, right? That is a rate of change of volume. So it sure feels like the equation we got to pull out of the hat is the volume formula for a cone. All right, who's got a deep hat and knows this volume formula? So 4/3 pi r cubed is a volume formula for a sphere. Okay, what if it were a cylinder? Would you know what the formula was then? So what's the formula for the volume of a cylinder? Okay, so we can copy that. There's a little space in the front. But the cylinder, yeah. So yeah, it's a 1/3 or an over 3. Which is kind of interesting that you could actually fit 3 cones inside of the cylinder of the same radius and height, like perfectly. 3 cones fit perfectly. You'd have to do some chopping up. But if you imagine, I'm going to draw this and then erase it in a second. But if you imagine the cylinder that this cone perfectly fits in, right? Imagine that cylinder. So we can clearly fit 1 cone, and then we have some more space left on the outside of the cone. Turns out that if we cut up 2 other cones, we can fit them in there perfectly. It's a 1/3 the volume of the whole thing. Okay. Good. All right, so we've got that formula there. So that's the formula for the volume of a cone. And so I guess we're ready to start symbolizing some stuff, right? What do we have here? This 2 cubic centimeters per minute. What is that? Symbolically, what is that?
That's H. DH over D.
Is it an H?
DH over D.
That's the volume changing, right? That's the rate of change of volume with respect to time. How fast is the level rising? That's what we're after. Let's symbolize that. That's the HDT that we want, yeah? Okay, so then when we look at this black equation for volume, the 1/3 pi r squared h, I mean, I guess we could use it for the volume of the whole cup, but really the cone that I'm thinking of is the cone with water in it, just the bottom part, right? Like that's the cone that we really need to focus on, this one that's changing. So, so I guess that means I still need to label something for my water. What should I label? Yeah, we need to have a name for this radius here. So the radius of the cone that has water in it. It's just a smaller cone. Okay, so I think we've got everything labeled here. We're good to go. So now it's time to take our original equation and do what? Take a derivative. Okay, what's the derivative of V? Normally would just be what? It would just be 1, and it is, so it's 1. But what do we tack on? dV dt. Equals. Okay, I see a 1/3, I see a pi, I see r, and I see h. R and h are varying, 1/3 and pi are constants. So do constant multiples stay or disappear? They stay. So I'm going to choose to put that 1/3 pi on the outside of whatever derivative calculation I'm about to do. And so I'm imagining parentheses around the r squared h, and I've just copied the 1/3 pi in the front. Okay, the derivative of r squared h. What rule do we need to use? It is a product rule. This is a product. R and h are both variables. So this is a product rule. So we go first times derivative of the second, copying the first, r squared, times, what's the derivative of h? Normally just 1. 1 dH dt. In this case, every single variable has t's embedded in it. Rest of the product rule, what's the next symbol? Plus. Second times derivative of the first. Second is h, times. What's the derivative of r squared normally? 2r, no problem, times dr dt. Because r is also changing with time. Okay, so I think we're good to go there. That's our derivative. So let's just start investigating this equation. I'm going to check off things that we know. dV dt, we know that? We know that, that's the 2. I'm not going to plug in just yet. 1/3 pi, no problem. R. Yeah, we're going to find the r, but I think we can find the r. We're about to fix the h at 5, 10, and 15, so like the h will get fixed. Probably we'll be able to figure out what the r is. So I'm going to check off these guys here. What about the dH dt? That's what we're after, so I'm quite happy that that's there. What about this dr dt? Is it mentioned in the problem? Is it what we're trying to find? No. So this gets a big old frowny face because I don't know what to do with it. I don't want it, I don't care about it, and I don't know what it is. And so it seems like we're really stuck. Like there's just this extra derivative, extra rate of change sitting in our equation. So it turns out that there was actually something we could have done to the original volume formula that would make our life easier. And that's what we're going to do right now. But I just wanted to make a quick pass. We took a derivative and we got this extra thing that we don't know and we don't want. And so maybe there's something else going on behind the scenes here. Take a look at the cone, and I'm going to draw a purple triangle, which is going to be that radius of 4 at the top, and then straight down, and then the rest of the side length. You don't need to draw that. And then I'm going to draw in blue a smaller triangle, which is the water level and the side of the cone, and then the water level. See the two triangles? What geometry word from your distant past? Those triangles are similar. Yeah? Same exact shape, different sizes. And so there's a relationship between the R and the H that we didn't take advantage of. So this is the time to do that. When you have similar triangles, you know that you can set up ratios and that they're always equal as long as you put things in corresponding spots. So for example, I could do the green R is to the 4, right? The small triangle side is to the same side in the big triangle as what is to what? It's the H, which is the height in the small triangle, is to the 16, the height of the big triangle. So that is an equation that is true. And so what can we do? Like, I just don't like the fact that this dr dt is here. And if I don't like the dr dt to be here, what needs to disappear up here is the r. Like, if the r is still left over, it's going to yield this ugly derivative. So I want to get rid of that r. Yeah, can we solve this guy for r and then replace? That's what we're going to do. So in this case, multiply the 4 and then reduce. So r is equal to h over 4. So we're going to say better is that v is equal to 1/3 times pi times, instead of r squared, what are we putting? H over 4. And that guy gets squared. So I get h cubed over 16, right? H squared over 16 and then times another h. And so just pushing all those constants to the front, pi over 48 h cubed, which is going to be far easier to take a derivative of. Everybody see where that came from? Speak up. 3 times 16 in the bottom, yeah. So that's our v. And now we're just taking a step back to find another derivative. We did it before, but we didn't like what we got. So let's do it again, but it's going to be so much easier down here. So derivative of v is just 1 dv dt. Pi over 48 stays or disappears? Stays. Derivative of h cubed normally, 3h squared. In this case, also gets the h dt. Okay, so we'll clean this up just a little bit. dv dt here, 3 and 48 reduce to 1 on top and 16 on the bottom. And so now we get to finally plug in the values of h that were given. Okay, so the first one, let's see, pi over 16 times, what's the first h that we're given? 5, so that becomes a 5 squared. The h dt, do we know it? That's what we want, so we'll copy it. dv dt, 2. That was given to us at the top. And then we do a little algebra, a little calculator stuff. Let's say like 0.23. What do we have? 0.4. How was I off by so much? Oh, I forgot the pi. Oh, wait. All right, what'd you get? 0.407? Okay, so about 0.4. Great. Yeah. Okay, so that's fine. 0.4, and then the units again are the h units over the t units. So centimeters per second. So at that moment, height is rising 0.4 centimeters. These guys said 0.4. I messed up on my calculation. I forgot the pi. Is there a question about this 0.4? Is it not right? Okay, so if we have calculator questions here, so we're taking 2, we're dividing it by a whole bunch of stuff. We're dividing it by pi over 16 and 5 squared, right? So I can just type that in as it is, pi over 16 times 5 squared. So that's taking 2 and dividing it by everything on the left-hand side. 0.407 is what I get. Okay. But since we've done all the hard work, we might as well reap the rewards by just quickly changing the h to, what's the next number? 10. So just change the h to a 10, and we'll get another answer. So we'll make a little table over here with our results. So h and dh dt, 5, 10, and 15, and we just found 0.407. So can somebody jump ahead and do the 15 part with the calculator? What do you have? Which one? 15.05. Yeah, the radius we eliminated. Yeah, we got rid of it entirely. Who's got this 10? Okay, does it agree with what we expected? These are all in centimeters per minute. So the height is changing by about 0.4 centimeters per minute in the beginning, and then only 0.1, and then only 0.5. As it gets very full, of course, it slows down. So once everybody's got that copied down, we'll take another look at the sketchpad example. All right, everybody got what they need? Okay, so here's here's the sketchpad thing. So conical tank, there it is. We're going to fill it with 2 cubic centimeters of water per minute. So it's hard to verify that the volume is changing by a constant rate. I can't really see that. Like my eyes look at other things, but I can't tell. But I trust Audrey, so we'll say that she's filling this thing at a constant rate of 2 cubic centimeters per minute. And what's happening to the height in the beginning? It moves really quick, and then of course very slow as it fills up, and that agrees with our intuition. So we can show the dHdt, h equals 5 That was at this moment, and it was where's the, here it is, at 0.407 centimeters per minute. And then we let the water rise up to 10. And then we're only down at 0.102. And then when we're at 15, almost entirely full at 0.045, which we rounded to 0.05. Questions on these? All right, sorry for the long demo today. So there's one more problem. We're going to skip it. You can try it later. Let's start the activity, which is actually part of your homework. So let me be clear on the homework. If you go to the next few pages, you will see a scanned set of problems. These are from another textbook. And so go just a couple of pages down the road, you'll find an answer key also scanned from that same book. And at the bottom below that scanned set of answers is the assignment. So the homework, which is you're going to start now as your activity, is to do these problems right here, 1, 3, 7, 9, etc. from the scan, okay? Everybody know what we're doing? There are also 2 problems from the textbook, but most of your homework is from the scanned set. Now, we know that these problems are long and they're hard. And again, we're spending another day on this coming Wednesday. We're going to do more related rates. Nothing new, just more problems, more variety. The entire homework assignment is not due until class 30, okay? That's Friday next week. Like, because they're tough and they're long, and so we're going to give you some time. So these are due Friday next week. And one other thing before you jump in, due on Monday is what? What is due on Monday from you? The test corrections. So make sure you get those test corrections. If you haven't done, put them in the folder. That's fine. But Monday, start of class is when they're due.